Section 8 of Chapter 7. Technically, this is the last section, Chapter 7, but remember, after this, we're actually going to do the last section, Chapter 6, which is the exact same thing as this, except with polynomials instead of exponential and logarithmic models. But today we're going to be curve fitting. Curve fitting, remember, is where we have data and we build equations from the data, sometimes by hand, but most of the time probably using a calculator. So let's take a look at our learning targets. The first one, I can model data by using exponential and logarithmic functions. You can create the models. The second one, I can use exponential and logarithmic models to analyze and predict. So once you've created the model, answer a question, because it will most likely ask you a question, and we'll see that. And so let's look at some data. The first question to ask ourselves, is it exponential? And that's the first question to ask ourselves because that's the first questions that they're going to be asking you. To tell if it's exponential, we can think back to the very beginning of this chapter. If we remember, if it's exponential, it doesn't have a common difference, but it has a common ratio. We can multiply from one thing, or we can multiply to get from one number to the next. So the first thing we need to look at is we do need to make sure that the x values are going up by the same amount each time. If these are jumbled, then we can't do it this way. We just have to graph it, look at the shape. But the x's are all going up by 1. Then we look at the y values. 5 times what equals 1? Sometimes, like in the beginning of the chapter, that was easy. Oh, times 2, times 3, times 1/2. This is times 1/5. An easier question than 5 times what equals 1 is just do the second one divided by the first one. 1 divided by 5. 1 divided by 5 equals 0.2. Then, -3 divided by 1 equals -3. These are already not the same. And if we keep going, -7 divided by -3 is +7/3, which is neither of those. And then we'll have 11/7, which is none of the above. So this one is definitely not exponential. In fact, if we look at it, we're not multiplying, we're just subtracting 4. -4, -4, -4. This is actually a linear model. So we're looking for these guys to be the same. So let's look at another one. The x's are going up by the same amount. Now let's look at the y's. 18 divided by 27 reduces to 2/3. 12 divided by 18 reduces to 2/3. 8 divided by 12 reduces to 2/3. 5 1/3 divided by 8 does in fact reduce to 2/3. We'd probably want to make it 15 16/3 divided by 8. You divide by 8 over 1. You can flip it, multiply by 1 over 8, and you do end up getting 2/3. And so this one is exponential because it has that common ratio of 2/3. And so when we have nice, pretty data like this, where you can see it comes from a math book, everything works out beautifully, we don't need a calculator to write an equation. If we go back to our equation, f of x equals ab to the x, this common ratio is b. So that's going to be 2/3. A is the y-intercept. Where would we find the y-intercept? Right in the table. That's A. Sometimes, maybe our table starts at 1, 2, 3. We'll go backwards 1 to figure out what 0 would be. But you can find this number right in the table. So we could write our equation, f of x equals 18 times 2/3 to the x. And so, you might be asking yourself, well, that's nice. It's all, like when the data comes out nice, that works. What if it doesn't come out nice? Well, that's what we're going to get to in the next slide. Before we get there, and the question doesn't really get asked all that much, at least not right now, but this is exponential. What if it asked if it was logarithmic? Remember that logarithms are inverses of exponentials. We switch the x's and the y's. If it was logarithmic, the y values would go up by the same amount, and the x values would have a common ratio. because it, again, just flips. So that's to deal with logarithmic, but I don't think it'll come up too much right now, so you shouldn't have to worry about it. So on to the not so pretty numbers. For that, we're going to do regression. And so if we have a problem, we have cooling T, we have data, we have time, we have degrees above room temperature. Now the x values do go up by the same amount each time, which is not particularly usual for real world data, but sometimes it is. You have years and you measure each year, it's going to go up by a certain number of years each time. So it's not unheard of. So we could look at our ratios. We could have 120 divided by 132 is about 0.909. 110 divided by 120, it's about 0.917. 101 divided by 110 is about 0.918. And 93 divided by 101 is about 0.921. And so you might be looking at those thinking, wow, those aren't the same. They're actually really close. For being real world data, that is remarkably close. Also, with exponential functions, there's rounding issues, and so that's going to throw those off. This is good enough for what we're doing. In fact, it's really good. Like if you had real world data that looked like this with a difference, that's something that you want to, that's something special. And so we're going to do regression. To do regression, you're going to want to get your calculator. So go ahead, get your calculator out. I'll wait. Participate in your own education. You have it yet? Still waiting. Yes, you don't think I'm talking to you. Get it out of your backpack. If you don't have one, well, you'll have to watch it or wait and do it in class. And these are the same steps that we've seen already. The first thing we need to do, we need to enter the data. And again, this is the calculator that I have. It's what we have in class. Your calculator might be different. The steps might be a little bit different. I'm sorry. This is what I have. So in order to enter the data, we're going to go to the stat menu. And so in the stat menu, we can go to edit and enter our data. Oh, look, my data is already here. You can enter your data as you're waiting. You can pause it if you need to, but then go ahead and enter it. The second thing we need to do is we need to graph the data. To do that, we go to stat plot, pick one of them. We're going to have to turn the plot on, make sure it's on scatter plot, make sure our lists are right. I have my data list 1, list 2, the mark, the color. Now, if we graphed it, we probably wouldn't see anything. So we're going to zoom stat. If we notice it's way down here at number 9, you could just choose number 9 instead of scrolling down, or you can scroll down. And we get that. It looks kind of like a line, but there is a curve to it. So we can see it's exponential. So the next step is to actually do the regression. So we want to quit out of there, then go to the stat menu again. Now go over to calc. This is where all the regressions are. We've already done linear regression and quadratic regression. Tomorrow we're doing cubic and quartic regression. We get another linear regression. It's the same as the first one. LN regression, that's logarithmic regression. The calculator does natural log. And then if we scroll down, the next one we'll see on the list is EXP-reg. That would be exponential regression. That's what we're going to use for this problem. And today, you're going to be using exponential and logarithmic regression, 9 and 10, or 9 and 0. It'll usually tell you which one to use, follow the directions. Make sure everything's entered right. List 1, list 2, nothing in frequency. Store regression equation, alpha trace to get to y1. That'll put our equation into y1 for us. Calculate. And there's our equation. It shows up just like they've always done. It tells us y equals a times b to the x. Gives us a equals 131.4. B equals 0.916. The r squared is how close does it fit. That's really close. I would write this down because when we look at the graph, it's going to go away. We'll get it written down in just a second. And so we check the graph as our fourth step, and it looks like it's going to hit it pretty perfectly. So it's always exciting when it's that close. And so that's how we do our regression. It's the same steps as always. That's, well, the calculator part of it at least. And so we have our equation written down. Don't just go 0.9. These decimals are huge. They do make a big difference. So we're on step 4. Check the graph. We checked it. It looked good. Now we go to step 5. Answer the question. All right, what did the question say? Blah, 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 blah. Find an exponential model for the data. Done. Notice it said exponential. We found exponential. If it says logarithmic, find a logarithmic. Now use the model to estimate how long it will take the tea to reach a temperature that is less than 40 degrees above room temperature. So, degrees above room temperature is y, so we need to plug 40 in for y. And now we just need to solve. We've been doing this for the past week. We're going to divide by this number. And 40 divided by 131.4 is just a number. It's about 0.304. I'm leaving that in my calculator. X is in the exponent. When you take the log of both sides, I'm choosing to take the natural log of both sides. It doesn't matter. You could take the regular log. You could take the natural log. Your number in this step would be different, but once we divide, it'll be the same. So I have natural log. Natural log, notice the x came out in front. So now I can just divide by the natural log of 0.916. And then this is just a number. Natural log 0.304, which is in your calculator. Enter, divide by natural log 0.916. Enter, and you get x equals about 13.55 minutes. So just over 13.5 minutes, the temperature will be less than 40 degrees above room temperature. And that would be using it to solve a problem. There's only really 2 problems this could ask us. It could ask us about like 40 degrees, or it could ask us to predict what the temperature is going to be after 10 minutes, at which point we just plug 10 in for x, 0.916 to the 10th, enter, times 131.4. We've been doing this for a week, but remember the calculator stuff. That's the regression. That's something that we've done in the past, but it's been a while. We'll be doing it again tomorrow and then practicing it again the next day. So we'll get a lot of practice on this in the next couple days. Anyway, don't forget to comment, and I will see you in class.